Okay, we shall get. We are organizing as a part of our institute series of lectures, and we wanted to start from last Friday, but due to some observations from our side, we had to shift the first talk on Monday today. And it's a great pleasure to have Partha, who will talk about a covariant approach to lattice, which is working for quite some time now, and he will tell us more about it. Partha, please.
Okay, thanks. Thanks to the organizers for this nice initiative. Um, so I'll just jump into the subject. Let me begin by explaining what physical theories are. Um, so the physical world that we see around us has two main components, matter and forces. And because of these forces, we see the matter moving, and there's the dynamics, and the goal is to understand how to explain those observations using certain mathematical operations. So a physical theory is a set of mathematical operations and an intuitive understanding of how those mathematical operations are related to the physical system. And this intuition is very important because the way it works that we develop physical theories from the ground up, which means we make some simple observations, try to come up with a simple mathematical model to explain that, and then we expand our horizon and include more and more complicated observations and make our physical theories more and more complicated as well. And in this this is a process of generalization, and in this process of generalization, the intuition, how the mathematical operations are related to the physical system, that plays a crucial role. So it is very important. So let me take an example. So you have seen footballs being played in the playground. If you kick it with a certain initial velocity, then it rises up to a maximum height and then falls back to the ground. And there is a particular type of trajectory. And the reason it doesn't go all the way, but it comes back, it turns back, is the fact that there's a force of gravity, which is a constant force acting at every point. It's a constant force at every point along the trajectory. And you can write a simple mathematical model to explain this. Now, if you, as I said, you expand your horizon and keep asking more and more complicated questions. So you can go from this picture in two different directions. In one direction, you could ask, the force of gravity is constant because it is very near to Earth's surface. So what happens if you go far away from Earth, so the solar system and even bigger length scales, how does the gravity play out in that length scales? You could also go in a different direction, look at the football itself very closely and ask what is it made up of, what is the microstructure, and those sort of questions. So we will explore, you will go in both the two directions and see where we reach. So let me start with the simplest physical theory, which is even simpler than the motion of the football, and that's a free particle. So here is a cartoon. So there is this is a space-time diagram. The whole three-dimensional space is represented by this slice, and you are shooting out a particle from this point with certain initial velocity. And as the particle moves, you are plotting its position against time, and you are going to get this in straight line. Now, since the particle is free, you don't expect the trajectory to change in a complicated manner, and therefore you should be having a straight line going through the origin like this. If you change the velocity, it will be a different straight line. Now, this general feature of this physical trajectory does not depend on where you start from, when you start, and what is the initial velocity. So all these features, they appear as some parameters in the physical trajectory, and different parameters are related by certain transformation. In this case, it is called a Galilean transformation. It's a space-time transformation. You can see that both space and time have translations. Within space, there is a rotation, and there you can give a boost. You can observe the motion while you are moving with a velocity, say u, and watch the particle moving, the general character of the physical trajectory will not change. So what it says is that if you start from a physical trajectory and give this transformation, you end up getting another physical trajectory, and that is why it is called a symmetry. Now, this description is simple and nice, but it is not suitable for generalizing it to more complicated situations. And in physics, what we do is to use a more sophisticated mathematical tool which generalizes much better than this description, and that's the action principle. It says that the physical trajectories are extrema of an action functional. So what is a functional? Usually we deal with function where in the input you give a number and you get a number back in the output. For a functional, in the input you give an entire function and in the output you get a number. So it is integral dt of L. L is called the Lagrangian, which is proportional to the Euclidean norm square of the velocity. So you need to, if you know the entire function x of t, then you can calculate the time derivative and therefore the Lagrangian, and then you have to integrate it to get the number. So you have to plot this number against the space of functions, and if you vary those functions, then the number will change. And the idea is to pick the right function for which under variation action will be an extremum. And so that particular trajectory is the right trajectory that describes the right physics. So that is the physical trajectory. Moreover, this action is invariant under the symmetry transformation. So you can check by inspection that this is invariant under these transformations. Now, symmetries are important because for every symmetry, there is a corresponding conserved quantity. In this case, the conserved quantity is the momentum or the velocity of the particle. And having conserved quantities means there are certain quantities which do not change in time, and the values help you classify all the physical trajectories. So this is a very powerful tool in understanding the physical motion. Okay. Now, if you go to the large distance path that we took, that we described earlier, what is the theory of gravity at a very large scale? This question was answered by Newton in 1687, but that description is valid only for slow movement of bodies, and it's called a non-relativistic description. This was generalized to relativistic description by Einstein in 1915, which could describe gravity in presence of when the motion of the bodies can be of high speed. It's called the general theory of relativity. According to this theory, gravity is described by the geometry of the space-time. So here is a cartoon. So in this picture on the left, you see there is no gravity, and the space-time is flat. Okay. When you put a mass in it, then it curves the space-time around it, and the geometry changes. And we know that the starting point of discussing geometry is to introduce a length square, and so the length square, which is and therefore there is a metric, and the metric is constant here, but the metric is non-trivially changing in this region where there is a massive object. So in the first example of free particle, if you have taken 2 points in this flat space, then we saw that it will be the physical trajectory is a straight line, because now the concept that you could generalize is the fact that the straight line is the trajectory of minimal length in flat space. So that is the concept that generalizes to a curved space. So here, in presence of a massive object, the space-time is curved, and given 2 points, say for example here and here, you have to ask what is the minimum length trajectory, and you find out after doing some calculation that the minimum length trajectory will be going around like this, pretty much the way the picture is suggesting. And that is the reason why small planets are moving around the sun in orbits. So that is how it is described in the geometric theory of gravity. Now, to know the physical trajectories, you need to know the geometry. Knowing the geometry means you need to know the metric, which is now a non-trivial function of x. So now our action principles should be such, our action should be such that while extremizing, the action is a functional of the metric g mu nu x, and when you extremize it, you should get the physical solution for the metric and therefore the geometry of the space-time. Now, there's a crucial difference here from the previous example. Earlier, we had the action was a functional of a function where that function was x of t. Now, this small x represents both t and the x vector. So this x vector goes into the argument, which means that at every value of the x vector, g mu nu is an independent function of t. So since x vector is continuously distributed, it's a continuum space-time, you have continuously distributed functions. It is not countable. Such a system is called a field theory, where you have a countable few degrees of freedom like this. It's called a mechanical problem, mechanical system. Here, it is not mechanical, it's a field theoretic system. And the action is such that the equation that comes out after extremizing it is very nonlinear. It's a nonlinear coupled differential equation, and it's very hard to solve analytically. So you could take a numerical approach, and that's what is done in numerical relativity. In order to do that, you have to replace the space-time by a grid, a lattice, so that your points of study become the points here on the lattice points, and therefore you make the variables countable, and then you use numerical techniques to solve the differential equation. Now let us go into this microscopic length. So there you find atoms and molecules. Now this is again a mechanical system, but of a different sort. So here's a picture of a hydrogen atom where you have a proton at the center and an electron is moving around it. But you see this picture is very different from, for example, Earth-Sun system, where you draw a trajectory for the Earth. There is no trajectory for the electron. And the reason is that although it's a mechanical system, the way the mechanics works is very different from the previous example. The previous example is something called classical mechanics. Here, the law of mechanics change. It's called quantum mechanics. And the difference is that in the classical mechanics, the path, the trajectory that extremizes the action is the only physical object to look at. But here, all the other paths, which are not even extremization of the action, also contribute. So each path, whatever path you could consider reasonably, should contribute to the physical calculation. So the mathematical operation involving the action is more complicated, and you have to take the average of all contributions from all the paths. And since it's an averaging procedure, you cannot calculate a particular trajectory, rather you calculate the probability density. And this plot shows the probability of finding the electron somewhere near the center. And there are two forces acting here. There's an electromagnetic attraction because proton is a positive and electron is a negative charge. And since the electron is moving, it tries to fly out, and that effectively acts like a repulsive force. So there are two forces. One is attractive and the other is repulsive, which are competing. And therefore, you would find only in certain locations the probability is high. You wouldn't find the probability to be large here, because here the repulsive force dominates and the electron is pushed away from the center. So this is how the mechanics works. But this is not the end. The problem is that this picture is again valid when the electron is moving very slowly. So it is not a relativistic picture. It is an analog of Newtonian gravity. The question is that how do you describe this quantum mechanical motion when the speed is very high? And physicists have found that at high speed, the description that's suitable is again a field theory, which where there are fields living in the space-time continuum, except that now it is not classical like the Einstein's general relativity, but it's quantum. So you have an action here, which is a functional of phi x, where this capital phi I have denoted by capital phi, the collection of all the fields that are possibly there. So for each particle, there is a field here. Electron, there is a field. For proton, there is a field. For the electromagnetic interaction, the electromagnetic field is also present. So collectively, I'm calling that capital phi. So the 2 points that I have to make here is that first of all, it's a field theory. It depends both on space and time and the continuum of degrees of freedom. And the second thing is that it is not enough to just extremize it. You have to take all possible such functions, calculate their averages, the average of their contributions, and calculate the probability amplitudes. That is how the calculation goes. But in this calculation, there is a problem of definition, and you can call it a problem of divergence, problem of definition. Basically, the fact is that this continuum, because of the continuum, the degrees of freedom are distributed continuously, and it is not straightforward to make sense of the averaging procedure. So here also you find the way out, which is latticizing the space-time, continuum space-time, and make these degrees of freedom that are appearing in this argument countable, and then you know a specific way of if you have countable things, then you can know how to take averages, and then finally you take the continuum limit. So so the conclusion is that the relativistic theory of all matter and forces are given by some action principle, where the action functional is a functional of the metric and all possible other matter and force fields. The difference between metric and these other force fields, fields phi, is that the metric is being treated classically and it gives nonlinear equations, and phi is treated quantum mechanically, which means you have to take average of all possible functions, not only one particular solution, and that's a problematic operation. And in both the problems are dealt with by taking a lattice, by replacing space-time continuum by a lattice. So you take x mu. Mu is 0, 1, 2, 3, 4 values for 4 space and time, and this x mu is replaced by x mu of p, p sub p, and p is basically for each value of mu, p mu is an integer, and a is the lattice spacing. So therefore, now the entire function that was continuous earlier is replaced by a discrete set of functions, g p of mu nu. Phi is replaced by phi p. So p is countable, and therefore your degrees of freedom are all countable. Now, once you do that, you have to answer 2 questions. One is that what is the theory that you are going to write on the lattice, which means given this physical theory that we somehow managed to understand what it is, what would be the corresponding lattice theory? What is the corresponding lattice action? And the second question is that once this lattice is a nice idea to do the computation, but once you do the computation, you have to finally go to the continuum limit, because that's what is physically relevant is. So how to take the continuum limit? And that's a very technical and difficult question. I'm not going to address that. I'll address only how to write the action on the lattice. I want to ask that question only. Now, if you have a term in this action which is some product of these fields, then it is straightforward. You just take the same term and put it on the lattice point, and the term appears in this action also. But if you have derivatives of these functions in this action appearing, then how do you deal with that? Because derivative is not defined on the lattice. So what you usually do is to replace the partial derivative by a difference operator. So if I have taken an example of a one-dimensional lattice, so phi p is a function on a one-dimensional lattice, and the difference operators are the forward and backward difference. They are just difference of phi between 2 consecutive lattice sites. This is what is usually done, and by doing so, the space-time symmetries that we talked about earlier, which I said is very important, those are lost. And the reason is that, so I tried to draw some cartoon pictures to explain the idea. So here you have a continuum. I have chosen one particular symmetry, a small translation along a certain direction. But there are other continuous symmetries that we talked about earlier. They are, all these statements are valid for them as well. So if you now give a small translation, this continuum moves here and they look pretty much the same. That's basically the symmetry of the space-time. And that is also reflected or inherited by the physical theory written on it. So the translation symmetry is there for the theory. However, if you take a lattice and give a small translation, then you end up getting this red lattice, which is not same as the blue one, old one, for an arbitrarily small translation. So the continuous symmetries are lost because this lattice does not match with the previous one. There are only some discrete transformations under which the lattice is invariant, is supposed to remain. Now, this is related. You can argue. I cannot go into those detailed discussions. This is related to the fact, in some sense, the breakdown of Leibniz rule of the difference operators. So, if you take delta plus minus, you can act on product of two fields, and you can show that they are not equal to this. They don't. The delta plus minus don't distribute in this fashion. Unlike the ordinary derivative does. Now, so I am thinking of another approach of looking at symmetries on the lattice in a different way, and which can preserve these continuous symmetries. And the approach is to think of lattice as a restriction of the continuum. So what I mean by that is the following. So this is the continuum example. Now you have the lattice, but it is not just, earlier I had only this lattice. Now I want to think of this lattice as a subset of a background continuum, some auxiliary. It's an imaginary construct. Okay, so there is a continuum whose restriction gives the lattice. Now, if you take this kind of a picture and then you give a small translation, the background continuum moves and the lattice moves with it, and these two looks pretty much the same. The situation does not change from the continuum case. This is how symmetry has to be thought, because this and this are looking similar. Now, if you think along this direction, this is how symmetry should work, and then turn that into some mathematical analysis, then it is equivalent to saying that the difference operator that you used for derivative has to be replaced by certain other derivative operator, where this is a logarithmic derivative d plus minus. It is related to delta plus minus in this way, and the right derivative operator is given by this linear combination, and you can check. You can show that both d plus and d minus satisfy Leibniz rule. So, although the lattice under an arbitrary continuous transformation is not invariant, but all the symmetry statements still will go through, and therefore conserved quantities will exist if you replace the ordinary derivative in the original continuum action by this derivative d, this discrete derivative d. Okay. Now the point is that this discrete derivative behaves exactly the same way as the ordinary derivative does in the continuum, and here are some list of its properties. So this is the linearity property, and this is just integral of total derivative of a periodic function being zero, that equation. And then I talked about Leibniz rule, and these are other properties of ordinary derivatives. They are still holding true for this discrete derivative. So this relation is for n integer, and then you can prove this. Then using this, you can extend this one to arbitrary m, any constant m. Now these first two properties are also satisfied by the difference operators delta plus minus, but delta plus minus do not satisfy these relations, which D satisfy. I mean, D plus and D minus both satisfy this kind of properties. You can explicitly verify these standard relations, like the action of D on a power. It's a power on the lattice, not on the continuum. It's XP. Okay. And there's an action on the exponential that you can calculate. This part is a logarithmic branch cut ambiguity. You have to choose the branch each time you calculate derivative on this exponential. The reason for this is that because XP is a lattice point, whether it is alpha XP or alpha plus this number times XP, you cannot distinguish here. So there is an ambiguity, and this is relevant. This ambiguity is not a bad news. Actually, I think it's a good news, because if the Leibniz rule is satisfied in position space, and if you go to the Fourier, if you do the Fourier transform, and then this D is going to act on the Fourier modes, and for each calculation you have to choose the branch properly. And it's only when you choose the branch in the right fashion, it is consistent with the Leibniz rule. Yeah, okay. So you basically, if you go to the momentum space calculation, you have to lay down the prescription of how to do the calculation. Once you follow that prescription properly, then it will always protect the Leibniz rule, and the usual symmetry consequences are expected to go through. Now, this property is very crucial. You remember, in the continuum, you have a Dirac delta function x minus y. Then the derivative with respect to x is negative of derivative with respect to y. This is analog of that on the lattice, where the Dirac delta is replaced by Kronecker delta. And this property is satisfied only by D, not by D plus and D minus. So D plus minus will satisfy all the other properties in this slide, not this one. This one, and also there are other distribution identities involving Dirac delta function. You can write down. We always use them in physics calculations. All those continuum identities will hold. Their discrete version will hold if you replace the delta function, Dirac delta function, by Kronecker delta, and the ordinary derivative of the continuum by this particular discrete derivative D. And this type of relations are extremely important for symmetry analysis, like calculation of Poisson brackets and stuff like that. So this is a very technical statement and only for the experts. This construction is understood so far for any action where G mu nu is a metric which is close to a space-time that is globally hyperbolic and whose Cauchy slices are conformally flat. And the generalization to other G mu nu, other backgrounds may be possible. I will not go into those details here. And the future is to look at, so usually we do numerical solutions, and also in the lattice quantum theory, we do the analysis without having any symmetries in mind. The question is that if you use this kind of an action and the resultant quantum theory or the equation of motion, whether the finding numerical solutions or the analysis in quantum theory, what kind of impact can they have because of the existence of these continuous symmetries. So that is being explored right now. So I will end there, and thanks for your attention.
Thanks, Partha, for this very interesting talk. And we are now, I already saw some comments. So if somebody would like to him directly, please unmute and ask it.
I have a question, short question, Bhaskaran.
Yes. Hi.
Yeah, please go ahead.
See, this construction of introducing logarithm to satisfy Leibniz rule, is it relevant in standard lattice gauge theories where you work in flat space-time? Is it useful there?
Yeah. Yeah. So if you just remove G mu nu, replace it by eta mu nu, the flat metric, then the statement still holds. But the point is that you can do for curved backgrounds also. If that background is globally hyperbolic and has Cauchy slices which are conformally flat, then also you can use it.
I see. So another short question. In condensed matter context, we're talking about some analog gravity. Defects
Sorry, what?
in condensed matter context, while talking about analog gravity, defects in a crystal behave like some non-trivial G mu, and you are keeping the lattice periodic, no defects, and you are putting a G mu which is position dependent. So can you comment on that? Can you go from one to the other? Hello?
I mean, yes, I mean, so G mu nu, if you start from the continuum theory, after constructing the lattice theory, G mu nu will depend on the lattice site. It will vary. So if that is the system, then it should work. The question is that in the condensed matter system, do you have a particular lattice to work with?
Yeah, you start with a particular lattice with defects like dislocations. Then when you look at matter living there, it looks as if in the long wavelength limit, the matter sees some gravitational, G mu.
So that is in a particular limit?
Yes, exactly. When lattice parameter becomes small or in the long wavelength.
Right. So you could ask, suppose you are starting with a lattice theory, and then you are taking a continuum limit and arguing that in the continuum limit it looks like a theory of gravity, or there is a metric.
Yeah, it's a defective lattice that you begin with.
Yeah. So the question that so I'm not see there you can write many lattice theories. See, all the usual lattice theories that are written in using the delta plus minus operator, if you use those or you use this D operator, all of them will give the same continuum limit. Naive continuum limit is same for all those things. So when you say that you get something in the continuum limit, that continuum limit does not specify or does not restrict what the lattice theory should be. So there can be many lattice theories which will give you the same continuum limit. So when you start out, you are starting out not with a continuum limit, but a specific lattice theory. That lattice theory may not match with this, with a lattice theory constructed out of this D operator, but one can check.
Thank you. Yeah, thank you.
Partha,
Yes.
can I ask a question?
Yeah, please.
Just how does the logarithmic derivative actually act on a field?
So this is log 1.
You expand the log and then consider?
Yes. Yeah. So this is log 1 plus delta. Yeah, it has a series in delta power.
Secular infinite series of differences taken.
Yes.
Sorry,
So,
can you
but if
please
you
show
take-
that slide where you defined it again? That might help understanding. Thanks.
Yeah. So this is the logarithm of 1 plus something. So you can expand in powers of plus minus delta plus minus. And so we know the action of delta plus minus on phi p or any field. And that is how you are supposed to take calculate. That is the formula for calculating it. But for practical, for example, for the polynomial, this is the result. You can calculate it. And if you calculate it using this expansion, I mean, if you demand this result, then there will be you will get an identity, and that identity is a complicated identity. I have checked that using Mathematica, but I don't have an analytic proof of those identities. But these are identities involving, say, Stirling numbers and stuff like that. For each of these this kind of claims, there is a corresponding identity to be satisfied. I mean, for example, here for D plus and D minus, and there's two separate calculations, and for each one of them, you will have some identities. But if you to answer further Sham's question, though it looks like an arbitrary situation, it is difficult to calculate because it is involving all the lattice sites and there are infinite number of terms. But if you go to the Fourier space, then you know the result. It is exactly the same result as is in the continuum. And there the calculation simplifies.
Okay. So in a sense, it is doing the average over all the differences, right? Because in the
actually, this is not easier. Actually, what happens is that, okay, I will tell you one thing. So I gave that picture argument. I started from that argument and I derived it, in fact. You can derive it. But then if you go to the, literature of difference calculus, this derivative appears. There, the approach is completely different. There, it is the ordinary derivative. This is the relation between ordinary derivative and difference operator. Okay, and the way that is derived is the same. Basically, what you demand is that every field in the lattice must be viewed as a restriction of the continuum, which means the derivative of a field is also a field, and that must also be thought as a restriction of the continuum. Now, in the continuum, derivative satisfy Leibniz rules. So you have to construct a derivative on the lattice that numerically matches with the continuum derivative.
Yeah.
And the solution to that question is this expression. And difference calculus literature I have checked. There is a method called operator method in the analysis of difference calculus. So this operator method basically uses this kind of thing, and there the usual ordinary derivative is the relation between the ordinary derivative and difference operator is derived, and it is this relation. There the approach is to look at this d as the ordinary derivative, and they are analyzing its relation with the difference operator. But what I'm saying is that for the lattice in this context, you don't look at this as an ordinary derivative. This is a derivative defined on the lattice, which will satisfy all the desired properties.
So are you able to recover the rotational symmetry is a two-dimensional lattice?
All of them, all the continuous symmetries, even the diffeomorphism will also be there if you choose the background that way.
Oh, I see. But just taking the definition and taking the limit a going to 0, I will not recover the continuum limit symmetries.
Okay, so there are two types, right? The global symmetries and local symmetries. Local symmetry means there is diffeomorphism. For the global symmetries, we have certain parameters, and the corresponding infinitesimal form can be written. Now, in the action, usually what we do is that phi x goes to phi prime of x prime, and that phi prime of x prime is a representation acting on phi x, and then you can then you go to define a delta 0 of phi, which is the variation of phi at the same point. There is no x prime, only at the same point. Using that, you can formulate symmetries. So don't in this case, in this calculation, don't talk about phi prime x prime at all. It is the delta phi at x, okay, and that has a specific expression in the continuum, under which if you take the variation action satisfies symmetry properties. If you look at that calculation only uses differential calculus and Stokes' law. Integral of total derivative is 0. Since the differential calculus will go through, the derivation will go through. And therefore you can have all this, the Noether's theorem coming out, because the calculation doesn't change, except that you are doing now it is the same amount of symmetry for global symmetries. But for local symmetries, for diffeomorphism, you have a vector field. That vector field is defined everywhere in the space-time. But here, it is the same diffeomorphism by a vector field, but the vector fields, the relevant vector fields that are giving deformation are the ones which are restricted to the lattice only. The points where there is no lattice point in the continuum, there is a vector field there. That also produces certain transformation. Those are omitted because those are not on the. So there is a reduction. So it's a redundant. It's a remnant of the original continuous symmetry.
Yeah, so when you construct the lattice action,
Huh.
do you use the logarithmic derivative? Say, for example, I want to consider gradient phi square term, usual continuum picture. If I want to put it on the lattice with the logarithmic derivative, what will I write? D plus phi square?
No, not d plus, d. The d plus
Oh.
d is half d plus minus d minus.
Oh, the D is D plus plus, what is it? I missed that.
Yeah. This one, this
Ah,
combination.
yeah, yeah, okay.
So there's only one. This d satisfies these equations.
Okay.
So you replace the ordinary derivative by this one. Sorry.
Okay, sorry, carry on. Thanks.
Yeah, you replace the ordinary derivative in the continuum by this d on the lattice.
Okay.
Are there any further questions? Please unmute yourself. I had one question. So, when you have these logarithmic derivatives, then the locality is not an issue, right? Because I think it's the mod of this operator falls exponentially fast in the infinity. So the non-locality will not quantum field theories.
Well, it is non-local in the lattice sense because it is involving all the lattice points.
Yeah, in the lattice also one needs to have algebraic fall of this modulus of the operator at large distances. So that is ensured here, right?
I haven't done that calculation, but it depends on what kind of functions you choose. So it can depend on that. All sorts of functions are not allowed because the logarithmic operation, the power series, has to exist. So, but if you allow the functions for which you can do Fourier transform, then the continuum Fourier transform calculation will go through here as this, in the same way, because on the Fourier mode it has the same action up to the logarithmic branch cut ambiguity. So if you take the continuum theory, go to the Fourier space, whatever way it looks, it will look the same way. The powers of k will be sprinkled around, but only on the lattice. Yeah, you take the finite lattice, so k is also latticized. Yeah, then, but that particular thing that you are saying, that mod square of the operator, I haven't checked that. I don't know.
Okay, thanks. Have any more questions? Or you can also put in your posts in the official Twitter post if you have more questions to.
I don't have a Twitter account, so I don't know how to.
I just
In the institute, yeah.
I just
Please go ahead.
I find this logarithmic, this logarithmic discrete derivative definition is very, very beautiful. Can you give me a reference for where I can find more about this?
Yeah, I mean, take any, I think any difference calculus literature will have it.
Okay.
See, the thing is very simple. You know, if you take phi p plus 1, the delta plus is difference between phi p plus 1 and phi p. Now, since you are thinking of this as a restriction of the continuum, it is like phi p plus 1 can be Taylor expanded around phi p. And that Taylor expansion is an exponential of the ordinary derivative. You can write it that way. And you just invert this relation. You invert then the ordinary derivative is logarithm of 1 plus delta. Okay?
Yeah.
Okay, so this is referred to as operator method in difference calculus. But it is not used in a crucial manner because the understanding is that this is the ordinary derivative and that this is the relation between ordinary derivative and difference operators. Okay, but for the lattice physical theory, I think there is a difference because you in order to calculate d, you do not need to know anything in the continuum. You need to know only, you need to pick values of phi p only because it is written in terms of delta plus minus. So this is a lattice these are lattice quantity, lattice derivative.
Interesting.
Okay, thanks. Very nice.
Okay.
Okay, so we end the session today. Nice questions. I'll leave it to end today. Thanks.